Most CAM workflows today still rely heavily on manual input. Programmers import the model, define features, create setups, select machining strategies, and validate the process largely by hand. That approach works, but it's time consuming, highly dependent on individual experience, and any change to the part often means revisiting a significant portion of that work. As part complexity and part counts increase, programming effort can quickly become a bottleneck. Automated CAM processing is designed to shift that workflow, particularly for families of parts that share similar features and machining requirements. The goal is to capture proven machining logic and shop standards up front and then apply them consistently and repeatedly across related parts and setups. In this video, you'll see that approach applied in practice. We'll start with a complete walkthrough on one representative part to establish the workflow at a high level, and then move more quickly through additional examples to show how the same automation framework can be reused across similar parts, even as those parts begin to differ. Let's walk through the first example. I'll start by launching the AutoTurn custom interface. This interface represents the front end of the automated CAM processing workflow and is configured specifically for this project. The first step is processing the CAD model. Here we select the solid model we want to run, and the system initializes a new ESPRIT project. As part of this step, the part is automatically positioned correctly in the workspace, so it's ready for feature analysis and downstream processing. Next, we apply the stock definition and run feature analysis. This ensures that downstream processing is based on the actual material condition, not just the nominal model. At this stage, the software is analyzing the solid model along with a defined stock and automatically identifying the turning and milling features required to machine the part. All the features you're seeing generated here would traditionally need to be defined manually by a programmer. The automation is building that foundation automatically and preparing those features for strategy application. You can see the feature structure being populated automatically. That's the groundwork for everything that's going to follow. With the part fully analyzed, we can move on to setup creation. The first setup is created automatically using the appropriate machine configuration. In this case, setup 1 is for a Haas lathe. The system starts a new ESPRIT project, places the part in the correct orientation, and brings forward only the features required for this setup. Next, we apply KBM, which stands for Knowledge Base Manager. KBM is where the machining logic lives. This is where predefined rules, strategies, and shop standards are automatically applied to the identified features. As this runs, the system is determining how each feature should be machined and generating the appropriate operations and toolpaths based on those established best practices. Manual programming for a part of this complexity can easily take most of a day. With KBM applied through automated CAM processing, that time is reduced to well under an hour. At this point, the core machining logic is in place. From here, we can apply the same automation approach to the remaining setups. Setup 2 is created using the same process. I'm speeding this up here, but the system is applying the same rules-based logic, filtered for the features and orientation required for this setup. Setups 3 and 4 follow the same automated process. The same rules-based logic is reused, with each setup created based on the features and orientation required. What's important to note here is that the automation logic is being reused, not recreated. As long as parts share a common feature structure, this same framework can be extended without rebuilding the process from scratch. With this approach in place, programming effort no longer scales linearly with the number of setups. The limiting factor becomes available machines and spindles, not how many programmers are needed to support the work. That completes the full workflow for this part. We've gone from importing the CAD model through feature analysis, setup creation, and rules-based machining, all driven by the same automation framework. The key takeaway here is that the upfront logic is built once and then reused consistently across setups to reduce programming effort and improve repeatability. Now that we've walked through the complete workflow in detail, I'm going to move more quickly through two additional examples. The first is a part that's closely related in terms of features and machining intent. The second introduces some variation, but still shares enough common structure for the same automation framework to be leveraged. The same automation framework is applied here, using the rules and strategies that were defined up front. This final example introduces more variation compared to the previous parts. While it's not a one-to-one family match, it still shares enough common features to take advantage of the same automation framework. In this case, the automation is extending the existing logic rather than starting from scratch. This is where ACP delivers the most value, capturing logic once and reusing it wherever common structure exists. To wrap things up, what you've seen here is automated CAM processing applied first in depth on a representative part and then extended across additional examples with varying levels of similarity. The common thread across all these is that the core machining logic is captured upfront and reused wherever feature structure and machining intent overlap. That's where the real value comes from, reducing repetitive manual programming while maintaining consistency and control. Automated CAM processing is best suited for families of parts with similar characteristics. But as shown here, even when variation is introduced, that upfront investment can still be leveraged rather than starting from scratch. From an executive standpoint, this changes where effort is spent. Programming no longer scales linearly with the number of setups or related parts. The limiting factor becomes available machines and spindles, not how many programmers are required to support production. While there is an upfront effort to build and validate the automation framework for a new part family, the majority of that work is done once. From there, the same framework can be extended across additional parts to drive efficiency, consistency, and scalability over time. That's the intent behind automated CAM processing, capturing machining logic once and reusing it wherever parts share common structure and machining intent. By shifting repetitive programming work into standardized framework, teams can maintain consistency, reduce effort, and scale more effectively as production grows. Thanks for watching.